So I posted the exam protocol. So as I announced, we will take the online exam for the midterm exam. And then for this midterm exam, you require to use lockdown browser. That's some specialized, specified browser. So actually, with the lockdown browser, you can only connect the Blackboard, and then you cannot use any other apps installed on your computers. Okay, so you need to use the lockdown browser, and then actually the exam questions will be shown through on the Blackboard. Okay, and then also we need to use the Zoom, and then so actually we are using Zoom meeting too. And then for during the exam, so we will use the Zoom for proctoring. So it's also I believe the protocol, the exam protocol mails were delivered to your mailbox. Okay, so you can find the detailed exam protocol. So please read the exam protocol article thoroughly. So it's very important. And then please be prepared for the online exam before exam start. Okay. Then if you have any issues or questions about the exam, please let us know. So us means so me and TAs. So let us know immediately. Okay. Yeah. So actually, also I missed another announcement. So actually, I will post the quiz. So it's a pub quiz. It's like a pub quiz, but I will use the lockdown browser for this quiz. So and then actually I will activate this lockdown browser quiz after this class, and then the deadline of the quiz will be about the Wednesday night. Okay, so and then in order to take this quiz, you need to use the lockdown browser. So that's just for make you be prepared. You prepared for the exam, the online exam. So you need to use the lockdown browser, and then in order to take the use the lockdown browser, then you need to turn on the webcam of your computer. So you need to turn on the webcam on your computer. Also, you need to use the Zoom meeting tool. So if you use the Zoom meeting tool on your smartphone, then the smartphone camera will be also turned on. So we can see you. You can see you while you are taking the exam. So actually you are right. Okay. Yeah, right. So this is an open book exam. So you can use any papers or some any materials or textbooks, okay, during the exam. But you cannot access the internet, okay? Also, during the exam, you cannot use any other electric devices. So for this slide, so please print the slide note we used during the class if you want to see the slide note during the exam. Okay. Okay, let's start today's class. So we are learning the chapter 4, the process architecture of this course. So as I mentioned in the previous class, so this is a very important topic. So in the chapter 2, we learned about the instruction set architecture. That is the interface between software and hardware. But in the in the chapter 2, so you learned about some basic computer instructions. So actually RISC-V instructions. So it's actually, it's like, it looks like software, not actual hardware, because, so what is the definition of this computer processor instruction? So instruction is given to the processor, then the processor generates the result of instructions. And these results are defined in instruction set architecture. So actually, if you can understand how the assembly code, assembly instructions of RISC-V work, then I believe you can solve some problems, or you can also understand how computer works with the instructions. Okay. But in chapter 4, we are learning about the process architecture. So process architecture means that this architecture defines how the computer hardware works. Okay. So when you learn about the instruction set architecture, this instruction set architecture just looks like this black box. Okay. The instruction set architecture define that the computer systems are just a black box that receive the instruction and generate the result defined in this instruction set architecture. So that's it. So what is missing? So I said that the time, processing time is missing. So that's why is this important? So instruction set architecture just define the input and output, but in reality, so we live in real world, and real world includes some time. So actually, in the computer hardware, it takes time to execute instructions. Okay, and then also when we build a computer system, then this computer system includes the hardware part, and then hardware part just actually define how computer systems really work. Okay, because the hardware is in real world. Actually, the software is in the fantasy world, not real world. So actually, the hardware exists in the real world. Okay, so in order to understand how computer works in the real world, then we need to understand the hardware architecture. And then in the chapter 4, we are learning how to build hardware architecture of processor. Okay. So we also learned how the instructions are executed, and then which steps are required in the computer processor. And then also we learned about some basic element of the computer hardware components. So we learned how to organize data paths. Also, you need to understand what data path is. So this is the definition of data path, the elements that process data and addresses in the CPU. Okay. So this data path is similar to the components, that's the hardware components inside of a computer processor. Okay. So and then this data path just processes data and addresses. Okay. Then what is the opposite concept of the data path? It's not opposite, and it's not opposite, but it's some comparative concept. It's the control signals. So we will learn about the control signals of a computer processor in this class. Okay. So in the previous class, we learned how to build instruction fetch step in the computer processor. Okay. So which components are required? So that means that which data path is required for the instruction fetch step. We need program counter register. So I call this is the register because the program counter value. I said the program counter is the address of an instruction. Okay, so this address data is stored in the program counter register. Okay, so and then with this PC value, the instruction memory is accessed. So you need to remember that if the memory is accessed using address, then the memory the data inside of the memory comes out from this memory component, okay, memory devices. Okay, so what is the input? The input of instruction memory is the read address. So address means the PC of an instruction, and then instruction comes out from this instruction memory. Okay, so actually in the lab assignment 2, you will be requested to design this data path. Okay, so you will be requested to design instruction memory, data memory, register file, and ALU. So those are representative data paths used in the processor. Okay. So in order to access the next instruction, we need to update the piece to PC plus 4. Why do we use this 4? Because the size of RISC-V instruction is 32 bit. And then also we learned that the RISC-V processor is byte addressable. So that means that the address 1 of the this RISC-V memory represents 1 byte size. Okay. So the size of the RISC-V instruction is 32 bit, that is 4 byte. So the piece of the next instruction is PC plus 4, except branch instruction. Okay. Okay. And then let's learn about the register file of the processor. So actually this register file stores the data in general purpose registers. Okay, in the chapter 2, and then we learned about the register operands. Okay, this data in these general purpose registers are used by R-type instructions, also any other instructions, such as actually most of the instructions use data in these general purpose registers. Okay, so in the chapter 2 we learned about the several types of instructions like R-type and I-type, so immediate type, and branch. So why do I mention these several types of instructions? So we need to know how many registers are used by these instructions. Okay, so for the R-type instructions, how many register operands are used? How many? It's 3. Okay, but yeah, so this is a real time. This is the what's that? How can I call it? So actually this Zoom is the real time class, but the one answer, so it's like so one direction lectures. Okay, okay, I understand. So for the R-type instructions, we require the instruction on an instruction requires 3 registers. So 2 source registers, RS. So, and then one RD, that means the destination register. And how about the I type? So I type requires, okay, two, right? Yeah, good. One source registers and one destination register. And then I type instruction use one immediate value. Okay. And how about the branch instructions, like conditional branch, like BQ? BQ requires two source registers. Okay, like BQ, X1, X2, and the target. So BQ reads data from two general purpose registers and then just compares these two data. Okay, so that's why BQ requires two source registers. So we need to design register file to support these types of instructions. So in this example, so R-type instructions requires two source registers and one destination register. So this is the maximum number of required registers, right? And then hardware need to support this maximum requirement. Okay. If hardware just supports this requirement, like one source registers and one destination register, then we need to access this hardware twice, because we need to get the two source in order to access the two source registers, we need to access the hardware twice. Okay, but for the better performance and efficiency, usually the hardware need to support some maximum requirement. Also, we already know that the R-type instructions are frequently used in the computer processor. So that means that the hardware need to support this maximum requirement. Why? We need make common case fast. Okay. So if the R-type instructions are frequently used, then we need to improve the performance of these R-type instructions. Okay, because those instructions are used frequently. Okay, so this is the maximum requirement for the register file. So this register file needs to support the two source register. That means that two register data read. So two read and one, this is the destination register. So one write. Okay. So actually the register file looks like a memory. Okay, that means that if the register number is given, so it's a register number is given, then the data corresponding to this register number is out. That is the structure and then the input and output ports of registers. Okay, and then I already explained that register file requires to have two reads and two write operations. So that means that this register file needs to receive two RS numbers, right? RS1, RS2 is a register number, and then one destination register number. Okay. Then, if the register file receives the source register numbers, then register file generate the output data for these source register numbers. Okay. And then for this destination register, that is the write operation. So write operation requires write data, right? Because this is the write operation. So For the write operation, we need the data input port for this write data. And then for this read operation, we need the read register number and read out port. Okay. So this figure shows the input and output ports of a register file. So that is also data path. So in order to support the 2 reads and 1 write operation, register file has 2 read register number, the read register 1 and read register 2, and then output port for the read out data. Okay, read data 1 and read data 2. So this data is connected to this register number 2, and then this data output is connected to this read register number 1. And then for 1 write operation, the register requires the write to register number and then write data. That is the input data. And that's it. Also, you can find the regular write port. That is the control port. So register file receives regular write control signal, and then that means that if this regular write is 1, then write operation is performed. Okay. And then this figure also shows the width of the read register 1 and read register 2 and write to register port. Okay. So what is the width? The width is 5. Why? Because there are 32 general purpose registers in RISC-V. Okay. That's why the register number width is 5 width. What is this? What is the width of write data and read data? Width is 64. Why? We are learning about 64-bit process architecture. Okay. And then in the chapter 2, so we learned that the data are processed by R-type instruction, and actually the data processed by R-type instruction and any other instructions have 64-bit width, because we are learning about the 64-bit processor architecture. So that means that the width of one register is also 64-bit. Okay. So that's why the write data port is the 64-bit width, and then read output has also 64-bit width. And that's it. That is the so this in this slide, so we define the input and output ports of register file. Also, we define how register file works based on the input signals and output signals, not based on input signals. Okay. Also, we define the control port of the register file, so regular write port. So as I explained, if the regular write signal becomes 1, then registers performs the write operation by these input. Okay. So understand? So we define the data path, the register data path, register file. Okay. So then how can we connect the instruction to this register file? So actually in this instruction fetch step, the instructions on instruction is out from instruction memory, and then the width of instruction is 32-bit. So this instruction is delivered to the register file, right? Why? Because for executing this instruction, we need to read data from register file. So we need to use the register operands. Okay. So let's see the R-type instruction of RISC-V. So in this R-type instruction format, we can find that RD is here, RS1 is here, RS2 is here. So it's pin number 31 to pin number 0. So that means that the instruction is out from the instruction memory, that this is the 31 to 0. So that means this is the pin number 31, and then this is the pin number 0. Then each bit is assigned to each bit field of this instruction. So what does that mean? So this instruction is out from the instruction memory, and then in order to access the register file, this part, and this part is connected to the input port of a register file. Okay. So this is the register file. This register file receives the two source register numbers, so read register 1 and read register 2, and one destination register number. So that means RS1 is connected to this port. Okay. RS2 is connected to this port. RD is connected to this port. Which part? This part, this part. RS1 is connected to read register 1. RS2 is connected to read register 2. RD is connected to write register here. Okay. Simple, right? So in this, among bits in instruction, these parts are directly connected to input ports of register file. Okay. Then how can we connect this read data 1, read data 2, and write data? I will explain later. Okay. Okay. And then let's think about the load store instructions. So load instruction looks like this. Offset. So in this load instruction, we can find, oh, this is the base address, and then this is the offset, and this is destination register. This is the RD, and then this is the actually immediate value. This is RS1. So which operation is required? So first, we need to access the register file. Why? Not to get base address from general purpose register here. So we need to access register file with RS1. So read, it's a read. And then which operation is required? We need to get immediate value from instruction. And the instruction, actually the immediate value is included in the instruction, and that is the 12-bit 2's complement number. So we can easily get this immediate value from instruction, and I will explain later. And then which operation is required? Add. Oops. Add operation is required because in order to calculate the target address of this load instruction, we need the RS1 plus immediate. So for this operation, we need the add operation. And then access memory. So this is the address is generated from the base register and immediate value, and then with this generated address, the memory is accessed. So memory, this is same to the, so this memory. So its address is here, and then data out is here, and then data in here. So its address is given, then data comes out from the memory. Okay. For 5, we need to write the data to destination register. Okay. RD. So actually write to RF register file with RD destination register. So those are the required operations for load instruction. And then for the store instruction, so actually this write, oops. So if we just mention, oops. For the store instruction, store instruction is a little bit different, but this part is it's not required. Oh, no. Oh, this is required. Sorry. So also for the store instruction, we need to calculate the target address. So actually we need the RS1, and then this is RS2. So actually the store instruction requires 2 source registers. That means that 2 read operations for register file. And then, so actually this step is not required, but additional step is required. So RS2 read. And then the data from the register file is stored to the memory. That is the store operation. So those are required operations by load and store instructions. So actually this address generation can be performed by ALU. Okay. Actually, we need to implement the add operation because RISC-V has add instruction. So actually this operation is already included in the ALU. And then the same operation can be used for generating addresses, because for this address generation, we need addition. Okay, so this hardware can be used for the, but which component is required? We need to access the memory. Okay. So we need to access the memory. So we need to implement data memory. Okay. And then for this data, in order to access the data memory, we need the address. Okay. So with this address, the target data can be accessed from the memory. Okay. And then for the load instruction, we need the read data port here. And then for the store instruction, we need the write data port. And then similar to register file, write data is the input port, and then read data is the output port. Okay. And then we need the 2 control signals, is the mem write and mem read control port. So memory read operation is performed when the mem read is 1, and then memory write operation is performed when the mem write is 1. So those are control port of the data memory. Okay. So So let's see the I format instruction of the RISC-V. So we can get source register from this field and then destination register from this field. So like this R format instruction is a 31 to 0. So these bits are directly connected to the write register port of register file. Okay. Also, the RS1 is directly connected to the read register 1 port of the register file. And how about the immediate field? So, as I explained, for this load and store instruction, we need to perform immediate plus RS1. Okay, and then I skipped this part in this slide. So actually, for the R-type instruction, we need to support the add for the add instruction sub, and then also exclusive or, and some logical instructions. So we need to support the arithmetic instructions and logical instructions for the R-type instruction. Like also the immediate instruction is also, we need to support the immediate type instructions. But for these various arithmetic or logical operations, we need the ALU, because ALU just it's very obvious, because ALU means the arithmetic logic unit. So that means that the arithmetic operations or logical operations required by instruction is executed by ALU. So if we just see the R-type instruction, this ALU received this read data from register file, right? So this is the 64-bit data. So directly connected to this ALU. And then also how about the second operand? So the read up port of the register file is directly connected to another input of ALU. So that means that this is the 64-bit, and then this is the 64-bit. Okay. And then also we need to select the appropriate operation of ALU by instruction, because the ALU needs to support the various operations like add, sub, exclusive, or AND operation. And then these operations are selected by this control signal. So this is the ALU operation signal. So based on this control signal and the control port, the operation mode of the ALU is determined. Okay. So this is the ALU, and then ALU generate the ALU result. Okay. So this is also 64-bit. So why do I mention ALU? Because in this loading, for the load and store instructions, we need to use the add operation supported by ALU. Then how about this load instruction? The load, in order to generate the address, the load instruction requires the data from register register 5, and then the second operand is immediate value. But for the R-type instruction, so when I explain about the R-type instruction, I explained that this output port of the RF register file is directly connected to one input of ALU, and then this port is directly connected to another input of ALU. So if these output ports are directly connected to two inputs of ALU, then we cannot use immediate value. Okay, so how can we use the immediate value? So the second input of ALU can have two types of data. So the first type is the register data, and the second type is the immediate value. So there are two types of data, and then we need to select from these two types of data. We need multiplexer, who are called mux. And then if we use the mux, then we also need the selection signal here. And then based on this selection signal, the output of a multiplexer is determined. So the second input of the ALU can be the data from register file and or immediate value from instruction. Okay. Okay. So also I mentioned that the data width of this ALU input is 64-bit, and then this is also 64-bit. So that means that this immediate value should be also 64-bit. Okay, but we already know that the immediate field of this I-type instruction is 12 bits. So 2's complement. So in order to use this immediate value, we need the immediate generator, and then this immediate generator just extends the bit width of the immediate value. So for example, the 12 bits of immediate value of load instruction is extended to the 64-bit 64-bit data. Okay, so how can you extend the this immediate value? You can just repeat the MSB of the immediate value, because the MSB just represent the sign bits of this 12-bit immediate value. Okay. Well, you may ask a question like that. In this figure, this is the 32 bits. So, but this 32 bit immediate value is extended to the 64-bit immediate value. But I mentioned that the load instruction used the 12-bit immediate value. So why is this 32? So actually, this 32 just to represent the width of instruction, because there are various assignment of the immediate value to the RISC-V instructions, and also, so we used some various types of immediate values, like immediate value from branch instructions, also immediate values from jump instructions. So then this cannot be specified by this 12-bit data. So we just use the 32-bit because the instructions are just used as the input of the immediate generator. Okay, so that's why we use the 32 for this width of the input of immediate generator. Okay. Okay, so until now we covers several data paths, like for the instruction fetch step, instruction decode step, that is, so instruction fetch step. So for this instruction fetch step, we need PC and instruction memory, and then instruction for the instruction decode step, we need the register file, And then execution step, we need the ALU. And then memory step, we need data memory. Okay. And then also the processor need to support the branch instruction. Okay. So actually in this chapter, we just support the BQ instruction. So what is the definition of the BQ instruction? And then target. So the definition of a BQ instruction means that the processor reads the two data from the register file, and then if the data of these two register files are the same, then the program jumps to the target of the BQ. Okay, then what is required? So we need to read, first we need to read the two source registers. Okay, so we need to access the register file for the two source registers. Okay, and then we need the comparison operation. But how can we perform the comparison operation? So in order to check the equality of A and B, we need to perform A minus B. So actually we need the subtract operations. And then actually this subtract operations is supported by ALU. Why? This 5 has sub instruction. Okay. So actually this comparison is performed by ALU. And then we can perform A minus B. And then we need to check the result of A minus B is 0 or not. So what is it? We need the 0 detection. Zero detection. Okay. And then this 0 detection can be performed by ALU also, because ALU performs the A minus B. And then actually 0 detection is very simple. We use the NOR gate. Okay. And then if A minus B equal 0, then PC is updated by current PC plus immediate field of conditional branch at but this immediate value is shifted to right by 1. Okay, so we need to support this operation. So what operation is required? We need to add this shift operation and add operation. So can you use the ALU for this add operation? Can you use the ALU? No. Why? Yeah, no. The answer is no. Why? Because we already use ALU for comparison. Okay. So actually for this branch instruction, we need the additional adder. Okay, because ALU is already used for comparison. And then also we need the shift left operation for this in order to generate the immediate value for branch instruction. Okay, and then this PC is updated by this result of PC plus immediate left shift by 1. Okay, so this hardware is required for branch instruction. So let's see how to build data path for branch instruction, actually BQ. So for this BQ instruction, BQ RS1, RS2, oops. Immediate. So actually we need to access the register file with the RS1 and RS2. And then this data comes, the two data come out from register file. So read data 1 and read data 2. And then this data is delivered to the ALU for the A-B operation. And then this subtraction operation is performed by ALU, and then we need to check the result is 0 or not. Okay, so we need to check the 0. And then, so this is the required operation for BQ. And then we need to also calculate the PC plus immediate value left shift 1. Okay, so we can use the immediate generator. Okay, so this immediate generator receives an instruction, and then the immediate generator read the immediate value from instruction and then generate the 64-bit immediate data. But for the branch operation, we need the shift left 1 operation. So it's just include 0 in the RSB part. Okay, so shift left 1, and then this immediate shift left by 1 is added to the PC, and then we use the additional adder here. So this becomes the PC plus immediate left shift 1. Okay, that is the required hardware for branch instruction. Okay, so actually, in order to create the hardware architecture of the single cycle processor, we need to combine what we learned until now. So what we learned about the instruction fetch step, instruction decoding step, and then ALU, the data memory accesses, and then branch instructions. So these all what we learned are all included in this single cycle processor design. Okay, so let's see the R type and then load and store data path. So we learned about the register file, and then this one output of the read data 1 is directly connected to this one input of the ALU, and then as I explained, the ALU can receive the one from register file and then another from immediate generator for the second input. So we need the MUX here, and then for the memory operation, the ALU generates the address, and then this address is directly connected to the address port of the data memory. And then also the ALU output can be the result of the R type instruction. Okay, so for this R type instruction, this is this output of the ALU should be connected to the write data port of the register file. And then for this connection, we need this bypassing route. Okay, So this write data can be from load instruction or R type instruction. That means that for the load instruction, the result data comes from data memory. And then for the R type instruction, the result data comes from ALU output. So we need to select. And then for this selection, we need multiplexer. That's why we need additional multiplexer here. And then this multiplexer select this write data. So write the data can be from memory or write data can be from ALU. Okay. So this multiplexer received two input data from data memory and ALU output, and then this output is selected by MEM2 reg control signal. Okay. Also, this multiplexer is controlled by ALU source control signal. So this figure shows the data path required for R type instruction and memory instructions. Okay. And then let's see the full data path of this processor. Actually, we learned about this part. Okay. And then the instruction fetch step and the branch instruction, the required data path for the conditional branch instruction is included. Okay. So for the instruction fetch stage, we need the instruction memory, and I already explained how the instruction memory is connected to the register file. Then this instruction is directly connected to the immediate generator. It is because the immediate value is included in the instruction directly. Also, I already explained that how the branch instruction is executed, and then this part is also included. So for the next instruction, that is the next PC, can be PC plus 4. That is the normal next instruction. And then PC plus immediate left shift by 1. That is 4 from branch instruction, like a BQ. So we need to select from these two program counter values. So one is for PC plus 4, and then one is for PC plus left shift. Immediate value left shifted by 1. We need a selection. So that means we need multiplexer. Okay. So one input from multiplexer is PC plus 4 here, and then another input is here. Okay. There is a mux, and then also we need the selection control signal for mux. That is the PC source. So this figure shows the full data path for the single cycle processor. Also, in this figure, you can find that the blue letters, like that, these blue letters means control signals. So also we need several control signals to build this single cycle processor. Okay. So we can find the link here, 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 here. So what did we learn? We first start from the required steps for executing instructions. Okay. And then based on these required steps for executing instructions, we first build data path. That means the required hardware components. Okay, so we learned that instruction memory is required. The register file is required, and then also ALU is required for all type instruction, and actually no more instructions. Then data memory is required, and then also we learned that the additional hardware such as this add and then the multiplexers are required. Okay, and then also we connect the input and output ports of each data path based on the required steps for executing instructions. Okay, so instruction is fetched from the instruction memory, and then after this step, we need to access the register file, and then in order to access the register file, we need which information is required. We need the source register numbers or byte register numbers. This data is already included in the instruction. So the instruction that comes out from instruction memory is connected to the input port of registers. So we define the connections between data paths. Okay. And then these data paths components require control signals based on the different operations by different instructions. Okay. For example, for this ALU, the second input of the ALU can come from register file or can come from immediate generator for load, or this is for all type instruction. Okay. So for these different operations or different paths, data paths, we need to select from two different data connections. That means we need the multiplexer. And then also we need the selection signal. So this is the control signals. Okay. So just to remember what we did for this hardware architecture, to build the hardware architecture. So we define the required steps, we define the required hardware data path or data hardware components, and then we connect the input and output ports of each data path. So based on some different operations, we include the multiplexers. Then also we define the control signals for each data path. Okay. So okay, I hope everyone can understand. Okay. Now let's learn about the control signals. Okay. So until this slide, we define how to connect the data path. So, but what is the missing? The missing part is the control signals, like this one. So that means we need to generate the control signals for appropriate operation of data path. Okay. So that's why we need the control unit that is called the control unit. So sometimes we call this is CU because control unit. And then these control signals are generated from this control unit. And then what is the input of this control unit? Input of a control unit is instruction. Why? Based on different instruction, we need to generate the different control signals. So what is the required control signals? We need the leg right control signal, and then this is the ALU source. Then memread and memwrite. So we need to select the branch instruction. So like the PC, the next PC. Also, we need to select the operation mode of ALU. So these are the required control signals, okay? And then I said that, oh, these control signals are generated from the instruction. Why? So for example, let's see the load and store instruction. For this leg write, the load instruction requires the register write operation for register file, right? Because the load instruction has the destination register. But how about the store instruction? Store instruction does not have any destination register. So that means that this store instruction does not require register write operation. So what does that mean? For the load instruction, we need to set the reg write as 1. But for the store instruction, we need to set the reg write as 0. So that means the control signal is determined by instructions. That's why the control unit receives instruction from instruction memory. So based on the different instructions, control signal generate the different control signals. Okay. 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 We need additional time. So then let's see how to generate some very important control signals like ALU operation. So I said that ALU is the arithmetic logic unit. So that means the ALU supports the various operations defined by various instructions. So for example, ALU needs to support the different arithmetic operations. Also, ALU needs to support the different logical operations. And then for this code, actually for this example, we just support the several instructions like add, subtract, and or instruction. Okay, so that means the ALU need to support the add, or, subtraction, and AND operation. Okay, we just need to support the 4 different operations with ALU. So we define this ALU operation based on the ALU control signal. So you may think that, oh, we just need the 2-bit control signals because ALU has 4 different operation mode. But so in this example, we use the 4-bit control signals because so actually the RISC-V has various other instructions. Okay, so in this chapter, we just support the 4 different instructions like AND, add, sub, AND, and OR instructions. But actually, RISC-V, the baseline RISC-V processor supports the other different instructions. Okay, like exclusive OR, and then or shift operations, some other different instructions. So that's why the common RISC-V processor has 4-bit ALU control bit, but in this example, we just support the 4 different operation modes. So that means we need just the 2-bit control signals. But in this example, we use the 4-bit control signals because the conventional RISC-V processor requires 4-bit control signals for ALU. Okay. Also, ALU need to support the add operation for load and store instructions, and subtracting operations for branch instruction, like because we just support the BQ, and then various operations for R type instruction. Okay, so we need to generate the ALU control signals based on these different instructions. Okay. Okay. So this slide shows how to generate the ALU control signals. Okay. So first we create the ALU OP signal based on the types of instruction. Okay. So ALU need to support the memory operations, memory instructions like load and store instruction, and then branch instruction, PQ, and the other R type instructions. So based on the different instruction types, the ALU OP control signal is determined. So for the memory instructions like load and store instruction, the ALU OP is set as the 0, 0, 0. And then for the branch instructions, the ALU OP is set as the 0, 1. Okay. And then for the R type instructions, ALU OP is set as the 1, 0. So ALU supports the 3 different instruction mode, like memory instructions, branch instructions, and normal R type instructions. So based on these different types of instructions, the ALU OP control signals are determined. And then this different ALU OP mode is determined by OP code field. So because for the load instruction, the OP code field is the 000011, and then for the store instruction, OP code field is 010011. And then for the branch, so here. Then for the R type instruction, OP code field is like here. Okay, so what does that mean? When the instruction is given to the control unit, we just check the OP code field of the instruction, and then based on this OP code field, the ALU OP mode, operation mode is determined. Right? So actually, I made this Excel table based on the different RISC-V instructions. And then if you see that this RISC-V different instructions, you can find the OP code field here, and then function 3 field here, function 7 field here. So actually, in this example, we just support the several instructions, but actually the baseline RISC-V supports the various different many other instructions. So actually for this load instruction, we just support the different data size for the different load instruction like LB, LH, LW, blah, blah, blah. And then we can find that for this various load instruction, OP code field has the various load instructions have the same OP code field 000011. So that means that if we just see the OP code field like 000011, so we can know that, oh, this instruction is load instruction. And this is the same for the store instruction. If we just see that, oh, 01110011, then we can find, oh, this is the store instruction. Okay. It's same to the branch instruction here. So 110011, then we can find that, oh, this is the conditional branch instruction. Okay. So the OP code field is the 01100011. So we can find, oh, this is the normal R type instruction. That means that requires the normal arithmetic or logical operation. Then if the OP code is 001, 0011, then we can know that, oh, this is the normal I-type instruction. That means normal arithmetic or logical instruction, I-type logic, arithmetic and logical instruction. So that's why, based on the instruction type, the ALU OP signal is determined by some instruction types like memory, conditional branch, and then normal R-type instruction based on the OP code field. Okay, we first generate this ALU OP field, OP control signal, and then based on the various ALU function, the ALU control bits are generated. Okay, so actually I will re-explain this part in the next class because we don't have enough time. Okay, so okay, and then but just to remember how to build this hardware architecture. And then just to remember the what step is required for build the hardware architecture. And then the last part is to the last part is building control signals. Okay. So in the next class, we'll complete this single-sided process design, and then actually the midterm will be included this until this single-sided process design. Okay. Okay, I'll stop here. And do you have any questions? Okay, thank you for your attention and see you in the next class.